Here's a question. You hand me a normal number, and I have to write it the old Roman way, with letters. How? Take 3,749. There's exactly one correct Roman spelling for it, and our job is to build that string. First, the alphabet. 7 symbols. I is 1, V is 5, X is 10, and it climbs all the way up to M, 1,000. The big rule. You write a number from its largest chunk down to its smallest. 3,000, then 700, then 40, then 9. But 4 and 9 break the pattern. 4 isn't 4 ones, it's 1 before 5, and 9 is 1 before 10. So how would you do this by hand? Pause a second. Most likely you go one digit at a time. Start with the ones digit, 9. You'd write a little routine. If it's 9, output 1 before 10. If it's 4, 1 before 5. Then the tens digit needs its own routine. 40 and 90 carry their own subtractive pairs. Same shape, different letters. Then hundreds. Then thousands. 4 near identical routines, and every one of them hides its own 4 and 9 trap. It works, but it's fragile. Forget one subtractive pair, like the 40 case, and a whole band of numbers comes out wrong. Now put those 4 routines side by side. They all do the very same thing. Take the biggest piece you can, write it, repeat. So why keep them apart? What if 4 and 9 weren't special at all, just more entries in one single list? Here's the move. Build one table of value and symbol pairs. Drop the subtractive forms right in. 900, 400, 90, 40, 4. Think of it like paying with coins. You have fixed denominations, and you always hand over the largest coin that still fits. You might be tempted to keep only the 7 base symbols and handle 4 and 9 yourself. Don't. List all 13 entries instead. The table runs biggest to smallest, so the rule is simple. Take the largest value that fits, write its symbol, subtract, repeat. Let's run it on 3749. Start at the top of the table, value 1000. Does 1000 fit? Yes. Write M, subtract 1000, leaving 2749. 1000 still fits, so write M again, then again. Now we're at 749. 749 is below 900, so skip that row. 500? That one fits. Write D, subtract, and we land on 249. Next, 100. It fits in 249, so write C down to 149. It still fits, write C again, leaving 49. 90 is too big for 49. 50 is too big. But 40 fits. Write the 40 pair, and 49 drops to 9. 10 is too big for 9. Then comes the 9 entry. 9 fits exactly. Write its pair, subtract, and num hits 0. Num is 0, so we stop. Stitch the symbols together in order, and that's the answer we were aiming for. Notice what we never did. We never checked for 4 or 9. Those subtractive entries sat in the table like any other value, and the same greedy step handled them. The table is always 13 rows. The number tops out at 39999, so the loop drains it in a bounded number of steps. So the work doesn't grow with the input at all. Both the time and the memory stay flat, constant on both counts. Same logic now in Python. The class and method names match the starter exactly. Here's the heart of it. One dictionary, each value mapped to its symbol, ordered biggest to smallest, subtractive forms included. An empty list to collect symbols. Then we walk the table from the top, the largest value first. The while loop is the greedy part. As long as the value still fits, append its symbol and subtract it off. When the table is done, num is 0. Join the collected symbols into one string and hand it back. And that's the pattern. When special cases start piling up, fold them into your data. The table did the thinking for us.